Can you check? Is it live? You are live, right?
I don't think.
Yeah, it's live.
Okay. So we can start at it. Okay. So we are going to start now.
Yeah.
Uh, Good morning, everyone. Uh, a very warm welcome to today's session of Assam AI Initiative Lecture Series. Uh, Today, actually, it's my pleasure to introduce speaker, uh, our speaker, Dr. Ayush Tripathi, who is currently at IIT Indore as assistant professor. And he is going to deliver a talk on DeMoAiR, that is about like about like multimodal air writing recognition for smart wearables. I'll just briefly talk about his what he has done and then what he is doing currently. Dr. Tripathi is currently as an assistant professor in the Department of Electrical Engineering at IIT Indore, where he leads the computational signal informatics and exploration lab. His research focus on biomedical signal processing and AI applications in healthcare, spanning brain-computer interface, human-machine interfaces, doing EEG analysis, automated sleep analysis, pathological speech processing. Dr. Tripathi earned his Ph.D. from IIT Delhi and went on to pursue doctoral research at Harvard Medical School, where he explored AI-driven healthcare technologies before joining academia. He also worked in TCS Innovation Research and Innovation, and he did his B.Tech from VNIT Nagpur. And in today's talk, Ayush will introduce us to the Airwriting, where we can do this writing in the free space using our nasal finger movements, and discuss how easy EMG and these IMU signals can be combined in a multimodal deep learning framework for real-time recognition. His works highlight the potential of AI writing as a user-friendly and hands-free input method for next-generation smart wearables. Uh, Now, let me welcome now Ayush on this I stage. Ayush, you can take over and you can start your presentation.
Yeah. So thank you so much for the introduction and for inviting me for the talk. So I'll just share my screen. So is my presentation visible now?
Yes.
Okay. So hello everyone. I am Ayush Tripathi. I'm an assistant professor in the Department of Electrical Engineering at IIT Indore. And today, my talk will be on DeMoAiR, which is deep learning based multimodal AI writing recognition for smart variables. So we'll talk about the motivation, introduction, and the different things we did. So before starting, I would like to give an acknowledgement that this entire talk is based on my Ph.D. thesis titled DeMoAiR, deep learning based multimodal AI writing recognition for smart variables, which was supervised by Dr. Lalan Kumar at IIT Delhi and Dr. Pratosh Shippy at ISC Bangalore. So this is the outline. I'll just introduce and give the problem statement, and then we'll go through each of these individual works, and then I'll conclude with some future directions and so on. Uh, first of all, if we talk about the motivation of this work, as we all know that communication is one of the most important life skills that we humans possess. So this is what makes us human. So the we are in daily life we are interacting with the colleagues, friends, family, and so on. But as we all know that these days there has been a rapid increase in the use of digital devices like computers, laptops, tablets, phones, smart wearables, and all that. So because of that, our interaction with the digital world has increased. So we are nowadays we are for doing anything we have to. Uh, so I think someone is saying that they're unable to see the slides. That our
Yeah,
interaction.
not able to see the slides.
So are the slides visible now?
Yes, yes, now it is visible.
Okay, sorry. Okay, so sorry for the slip up. So again, I'll just give a note that this is based on my PhD thesis titled DeMoAiR, Deep Learning Based Multimodal Air Writing Recognition for Smart Wearables, where I was supervised by Dr. Lan Kumar and Dr. Pratosh AP. So to motivate, so as I said, communication is one of the most important life skills, and these days we are using a lot of digital devices like mobile phones, laptops, and VR headsets, and so on. And even to communicate with our friends and family and colleagues, we are using digital devices. So, however, the input method that the way we give input to these devices still have largely remained traditional, and not much innovation has been taken care in that regard. For example, we still use keyboard, mouse, touchscreen, all these which have been around for quite some time. The next generation of technology is aimed at eliminating the need of these mediating physical devices. So, for example, if someone is using a VR headset, we cannot connect a mouse or a keyboard to a VR headset. So, we need to look for alternate methods as well. And we also need to search for tools that can get integrated as extension of our own cognitions, and we can connect seamlessly with the digital world. Uh, for example, there was a survey by Ericsson cited below, uh, which in which like 43% of the people who were surveyed, they believe that in near future smartphones can be replaced by wearables, and already wearables are being used for a lot of different things like fitness tracking, health tracking, safety, and so on. So the variables are already being used for a lot of different things, and all of us have had some of the other exposure of wearable devices like smart watches, smart bands, and so on. Now let us like look at some use cases where we need some alternate mode of communication. So, for example, if you look at a VR headset, so how do we give input to a VR headset? I mean, because the output is directly projected into the eyes of the user, so there cannot be a keyboard or a mouse or a touch screen that one can use to give input to such a device. So there can be different solutions. For example, speech recognition systems are quite popular. So where one can speak and then that can get converted into text, and then that can be used as an input command to the VR headset. There is gesture recognition. So people use some devices, they hold those devices in the hand, and based on the movement, some input can be given to the VR headset by using motion sensors and so on. But there is no one solution. Uh, so if you look at speech as an alternate means of communication, but that is one viable solution. But speech, there is a large section of population that suffers from some or the other speaking disabilities, and also because of different kind of accents and different languages, there's a uh, uh, scenario where the automatic speech recognition engines, they fail to perform as good as they would do for like the things that they're trained on. For example, some particular accent of speech on which they're trained on, they perform well, but they sort of do not perform that great in out of accent cases. So one solution can be gesture recognition, where a person can learn some particular gestures for a particular device and then use those gestures, but then for each of these individual applications, one will have to learn a new set of gestures and then use that. So over time, for different applications, there will be different gestures. Also, speech in public places, speech may not be desirable because people may need privacy. Because suppose someone is in a metro or in a train station or airport, they might not want to speak. They might want some more silent method. So, to give an alternate method of input to these digital devices, we propose air writing as a solution, which essentially is like if we want to define air writing, it would be writing of letters or words with the hand movement in free space. So, if I'm writing something in the air with free movement, that is air writing. Essentially, it is a specialized case of gesture recognition, but here the vocabulary would be letters in a particular language. So For example, throughout this talk, I'll talk about English. So the gesture vocabulary is letters A to Z. But because a person will not have to learn anything new, and they are all like everyone is already familiar with A, B, C, D. We have all been doing it since we were a child. So we don't need to learn anything new to use such a system. Hence, we think that this would be a good alternative the traditional gesture recognition. So, however, like as simple as it may sound, it is not a very trivial task because the same letter can be written in different ways by different people. The pen lift movements are not visible in air writing, and also users don't have a sense of space, and then because of that, they tend to lose orientation while writing. So these are the different challenges. Uh, the way we formulated this problem is as follows. So we all know like writing is not a straightforward task. So there are multiple things that are happening. So first we have to think about what we have to write. Then our forearm muscles will move, will get activated. They'll bring about some motion, and that will eventually result in our wrist moving, which through which we will actually write the letter. So we can use cues from any of these individual aspects, from the brain, from the forearm muscles, or from the wrist, to try to identify what was written. So uh, we do a multimodal approach where we use electroencephalography or EEG for brain signals, electromyography or EMG for muscle signals, and we use a inertial measurement unit for looking at the wrist movement. So all these three modalities have the same information but a different view of those three information. Uh, the first, so these are the problem statements that we looked at. So first, we wanted to establish benchmark data sets for air writing using multiple modalities. Then do air writing recognition using these three individual modalities. Also look at fusion of these modalities if that could be used. So the major contributions are, we looked at, we established several benchmark data sets. We did IMU, EMG, and EEG based air writing recognition, and also looked at fusion of EMG and IMU. And also, after this talk, if anyone is interested, all the source codes and data sets we have made it publicly available and can be accessed using this GitHub repository. So I'll one by one move to these different works. So I'll start with IMU, the go to EMG, and then EEG. So the first work that I'll talk about today is called SCLARE, which is supervised contrastive learning for user and device independent air writing recognition. So, in this particular work, we tried to explore supervised contrastive learning based framework for identifying air writing using signals which we obtained from a RISC-V IMU. So, the essential idea is that the hidden representations for same letters. So, for example, if we have 2A or 2B, so the hidden representation would be similar to each other, while for different letters it will be apart. So we propose a two-stage classification approach where first we train an encoder using by minimizing what is called as the contrastive loss, and then in stage two we train a small classifier head by minimizing the cross entropy loss. And for IMU based air writing, we had a publicly available data set from 55 people writing A to Z 15 times. So we use that. And second, we record our own data set in the lab from 10 people, from 20 people, well, when we ask them to write A to Z 10 times each in the air. So this is the block diagram. So this is stage one where we have the input. Input looks something like this, where we have six signals. So these are three signals from the accelerometer. So while writing any alphabet, this is measuring the linear acceleration across x, y, and z direction. So that is the uh, three signals that we get from the accelerometer, and then three signals we get from the gyroscope, which is angular velocities across three dimensions, three axes x, y, and z. And then we minimize the contrastive loss. And then in stage two, we train a classifier head by minimizing the cross entropy loss. And then if by using this, so these are the two different data sets that we use. So one is from 55 subjects, as I said, while writing A to Z 15 times. Second one was 20 subjects, which was recorded in the lab in this kind of setting. And this was from 20 people, 10 times they wrote A to Z. And then we performed evaluation in two different settings. One is, if we do leave one subject out experiments on the first data set, and like the second one was leave one subject out in the second data set. So on these two different data sets, we achieved accuracies of about 88% and 86% for identifying these alphabets A to Z. Uh, and if we bring the if we have if we suppose take this representation from the encoder, and then we project it down to two dimensions, and then we plot for different alphabets in different colors. This is the kind of plot that we see. So we can observe that there are very tight clusters corresponding to different alphabets. And like what is interesting here is this sort of overlap between D and P alphabet. So because both D and P, when you write, it is essentially a vertical line with a semicircle. So the model finds it hard to differentiate between D and P. So that is what we can clearly observe here. And based on this work, we put a real-time demonstration where we try to identify. So I'll just share that. So here you'll see this is a person, that is me, wearing this band over here on my hand, and I'm writing in the air. And what this system will do is it'll identify what was written and then print it on this screen on the left. So this is the demonstration of this entire system that we developed uh, as a part of this. Next, our another goal was to look if we can further improve the performance of our system. So for that, we tried to look at the literature from the image classification, and there is like huge work in image classification, and there are tools which can like there are a lot of models that have been very successful in classifying different images. So we tried to look at a image-based framework where we converted these time series signals into corresponding image representations, and then we leveraged a lot of existing architectures such as ResNet, DenseNet, VGGNet, GoogleNet, and AlexNet, and different variants of these architectures to see if we can use this to improve the classification. So on both the datasets, we obtained slight performance improvement. So for the first dataset, as I mentioned, we were able to achieve an accuracy of 89%, about 89% for classification, and for the second one, about 85.36%. So this was in a nutshell the work that we did in recognizing air writing by using RISC-1 IMU or RISC-1 Inertial Measurement Unit. Moving on, we went to the next modality, which is the electromyography or EMG signals from the wrist. So here, our first objective was to create a data set, because unlike the air writing for RISC-1 IMU, for EMG there was no existing data set. So first we had to record a lot of data from different people in the lab, and then we evaluated different the performance of the writing real machine system by using different time and time frequency domain features as well as different deep learning architectures. And then we looked at two different scenarios. One is a user independent and a user dependent scenario, as I'll describe in a minute. So this was the entire data collection setup that we had in the lab. So we could see there are these different five different muscles. So when we are moving the wrist, so these are the five different forearm muscles that are most involved in this wrist motion. So we identified that, and this was done in collaboration with physiology department doctor from the All India Institute of Medical Sciences, AIMS, New Delhi. So we identified these five different muscles that are involved, and then we attached sensors to these, and then we asked a person to write in the air when these EMG signals were recorded from these five different locations. So we made this setup and we recorded data from 50 different people when we asked them to write English uppercase alphabets and 10 repetitions of these. And the sampling rate of this particular EMG was 2000 hertz. Uh, then, so as like we can imagine, like for different people, because this is data from 50 different people, uh, there is a large of length of signal. So I might take say 1.5 seconds to write A. Someone might be a slow writer and might take about 2 seconds, and so on. And then there are also different alphabets. So there's a different time. So this figure here is a histogram of the distribution of writing time in seconds, where the mean, median, and 99 percentile are shown in black, red, and green. So we what we wanted to do is we also wanted to look at what is the ideal length in which we can identify what was written. So if we could use just a 2 second long segment. So when suppose I'm using a 2 second long segment, I would if someone has written for longer duration, I would just discard those samples, and if someone has written for a smaller duration, we would add zeros to the end to make the length uniform. And we try to look at different lengths by using different interpolation techniques. Like we use four different interpolation techniques: linear, quadratic, nearest neighbor, and cubic interpolation to do this. Then we looked at different time domain features. So the row on top here is the raw EMG signal, which is quite noisy. So if you compare this with the IMU sort of signals, we can see that the IMU signals are quite clean. So when there is a motion, very cleanly it is visible, the points where there's a motion, that is very cleanly visible. But if we go to the EMG signal, we see that there is a lot of noise that creeps in because of the fact that there is because beyond that muscle layer there is a fat layer, then there is a skin, and on top of the skin these sensors are placed. So the signal essentially gets corrupted when it travels through these layers, leading to this sort of noisy nature. So we applied some bandpass filters, and then we extracted different time domain features like the mean absolute envelope, NUG envelope, variance envelope, and so on. So we can see that essentially converting this noisy signal into a sort of cleaner representation that we can use now to feed to the deep learning models. And we also looked at specifically two different time frequency domain features, which was the STFT image and the continuous wavelet transform image. Along with this, we used lots of models. So we used 1D CNN, LSTM, bidirectional LSTM with and without attention, and a combination of 1D CNN and LSTM based models. And we evaluated the model performance in two different settings. One is user dependent on top, and one is user independent. So the difference between user dependent and independent is in user dependent setting. We have taken 50 subjects. We have recorded data from 50 subjects at 10 repetitions. So in the user dependent setting, what will happen is we will take data from all 50 subjects and 8 repetitions to train the model, and we'll test the model on 50 subjects, the remaining 2 repetitions. So the model will see some user specific information, but not all. the test set will still be held out. In the user independent setting, we will train it on 40 subjects and test it on the remaining 10 subjects. So the model will not at all see any user information. So as one would expect, the performance of a user dependent model will always be better than a user independent one, because there are user specific patterns, during writing and so on. So the best accuracy here was 75.8% in user dependent and 61% in user independent setting. And by using the time frequency domain features, we were able to obtain 78.5% in user dependent and 62% in user independent. And then we also extensively looked at the effect of different parameters that like which are signal length, window length, and so on and so forth on the accuracy. This is the confusion matrix. So, if we look at what are the misclassifications, so the major misclassifications were again P and D, as we earlier talked about, are quite similar. So, P and D account for most of the disagreement, like here as well as here. The other ones were, for example, B and R. So for B, we have to write full B and R. So if we are using a shorter length of signal, then B and R can be misclassified as, because essentially for the first half, at least till the first vertical line in the first semicircle, B and R are similar. So that's where using a longer window is important. Next, we tried to improve upon the performance of this EMG-based air writing recognition system, where we use this model architecture by combining two different loss function. One is the triplet loss, which was used to learn the feature embeddings, and then using cross entropy loss minimization, we tried to identify which character was written. So we are simultaneously minimizing the triplet as well as cross entropy losses while feeding the okay. And the experiments were performed on the dataset that we collected in the lab. So, this is what the architecture looks like. So we have an anchor and we have a corresponding positive sample, which is from the same class as the anchor, and we have a negative sample, which is from a different class. And then the idea is that in the learned feature space, the anchor and positive embeddings should be close to each other. So the uh, anchor should attract the positive, and the anchor and negative embedding should be close to each other. So anchor should repel the negative. So that is the idea, and we use three different variations of triplet loss. So one is n pairs based triplet loss. So what we are doing here is we are using dot product as a measure of similarity between the embeddings, and what we want to do is we want to have the dot product between the anchor and positive, since they are close, it should be as small as possible. So this ZA dot ZP should be as small as possible, and then hence we are minimizing this thing. And then in the second one was margin based triplet loss. So again, we want the anchor and positive to be as close as possible. So this term ZA minus ZP should be as close to zero as possible, while this ZA minus ZN, the two norm of it, should be as high as possible. And similarly, we have a triplet loss, margin based triplet loss with cosine similarity, where the dot product between ZA and ZN should be as big as possible, and ZA dot ZP should be as small as possible, so on. And then in order to choose, so we have to choose these triplets. So like one way would be to make all possible triplet pairs, and then but then that would increase the computational complexity. So for that, we use three different techniques. One is easy positive mining, so where we choose the easiest positive in uh, for making the pair. Hard positive mining, where we choose the hardest positive, and semi hard, where we choose positive which is hard, but it is still closer to the anchor than it is from the negative, corresponding negative. And then similarly, we use easy, hard, and semi-hard negative mining as well. So after all this, and the encoder is a 1D CNN bilesteam based encoder. By performing all these different ablation experiments, we were able to improve the performance. So in user independent setting, if you remember from the last paper, it was around 62%, and here we were able to increase the accuracy by about 4% to around 66%, and in the user dependent setting to about 81%. Now, if we visualize, so similar to the IMU case, if we visualize these vectors, we would still see that there are these clusters. But again, if I take go back to the IMU based clusters, these were quite distinct. But these clusters here, in case of EMG based, are not that distinct. They are still there's a lot of overlap, and that is because of the noise that gets creeped in because of the fat layer and the skin layer. Next, we try to like do a small mini experiment where we try to fuse the IMU and EMG modalities for air writing recognition by using two different techniques. One is early fusion, and the other one is tensor fusion network. So early fusion essentially, so there is a encoder here for both IMU and EMG, and then we get a representation layer, and then we fuse these two by simple concatenation, and then try to minimize the cross entropy loss overall on that. And in the tensor fusion network, we take the outer product of the embeddings between the IMU and EMG embeddings, and then try to minimize the cross entropy loss overall. So we found that. There is only a very slight improvement that we observed. If we look at the only IMU case compared to the fusion case, there is only a very small improvement. Like from here, we can conclude that like using only IMU is sufficient, and add combining IMU and EMG modalities does not really boost the performance that much. Moving on, the final work of that I'll talk about today is called NeuroAir, where again we do air writing recognition, but by using EEG signals that we record from the brain. So, so this was again we recorded a lot of data in the lab where using this EEG cap, and we recorded data from 10 people when we asked them to write English uppercase alphabets 100 times by using this while wearing this 31 channel EEG recording device. Uh, and After this, we did a lot of EEG pre-processing steps, there's bandpass filtering, there's removal of artifacts from the eyes and muscle artifacts, and then we looked at different frequency bands of EEG like delta, theta, alpha, beta, and gamma bands. Uh, and Also tried to look at some source domain features. So this EEG, given this EEG data, we estimated the cortical current densities in the brain by using a combination of a forward model, which estimates the propagation of the how the neuron fires. There is a dipole that gets created, and how that dipole moment gets propagated through the different layers of the brain and the scalp to finally get the voltage at the electrodes. And then there is an inverse model by which we estimate these cortical source currents with the given forward model. So we also use these source domain features, and then we also decompose the EEG signal into spherical harmonics and head harmonics based features, which are so these two are essentially basis functions for any signal defined over a sphere or a head. So in terms of results, like the summary, I would say would be we used the different model architectures, and the overall accuracy that we observed was around the best accuracy was around 44% or so. Uh, like what we could say is, so although all these three different body parts are involved when we are writing, so from brain to forearm muscles to IMU, and that is the flow of information, but the level of noise is the lowest when we look at an IMU sensor. With EEG, with EMG, the noise further improves, and with EEG, there are also other factors because of which there is even more noise, and the accuracies go down in that order. So in conclusion, we recorded several different data sets, and we have also released those and explored IMU, EMG, and EEG based air writing recognition. And also we presented a real-time demonstration of the IMU based air writing. There is a lot of future scope in this. So, for example, we are yet to look at word level air writing recognition. Like we're still dealing only with isolated letters. So, for a true system to be deployable, we need to be able to identify words, and then no one like writes the words in all uppercase. We all use mixed case while writing. So, recognizing mixed cases is also another thing, plus numbers. And then also we are yet to have a real-time demonstration using EMG and EEG signals. We have done that using IMU, but not using others. And of course, like since like we're in India, we're a diverse country. We like English is not the only language, and we cannot using English. We cannot cater all the population. So we need to look at other languages as well, and integrate this with the smart wearables and VR headsets and so on. So these are some references. And also towards the end, I would like to say that right now at IIT Indore, there are PhD admissions open. So if anyone is interested in this sort of work or anything related to biomedical signals and AI, feel free to like go to the link and apply, and also drop me an email. I'm happy to contact. So thank you, everyone, and looking forward to any questions or any feedback.
Hello, Ayush.
Yeah,
Yeah.
yeah.
So it's wonderful talk actually, and especially like the idea of fusing and all those modalities and then getting the uh, results is very interesting. And let me check if there is any questions in YouTube chat. Just one second. Okay, so we don't have any questions in YouTube chat. So let me ask from a few questions from our that Excel this Google form we have shared. Okay.
Yeah, sure, sure.
So there are some basic questions are there. Okay. So of the first question actually they were asking is that mm, how to handle the synchronization. Like for example, you are using multi different modalities, EEG,
Mhm.
EMGs, and IMUs,
Yeah.
and then for example in the air this writing and all. So how to make it, how to synchronize and noise across such diverse biosignal modalities in real time.
Right, right, right. So, for now, for each of these three individual modalities, we looked at different noise handling mechanisms. So, for example, IMU, out of all these three, IMU would be the cleanest signal when we are moving the motion sensor picks that up very cleanly. So that happens very nicely. But with like for EMG, we need to apply some band pass filters and then some extract some time domain envelopes like a moving average envelope or so on. So that is definitely required. And for EEG, we have to even further go and do some art, because in EEG there are artifacts from the eyes, from the muscles, and so on. So we need to do such removals. So I would say even the time complexity also increases for each of these modalities. So, like for IMU, the time complexity would be low because the pre-processing required would be very low. For EMG, it would be slightly higher because the pre-processing required would be more, and for EEG, it would be even further more. So, in terms of offline, we can do it very nicely, but for online, like real-time demonstration with the IMU, we saw that it was fairly real time. Like we were able, like the lag was very low as I showed in the video demonstration. But with EMG, the lag will slightly increase because of the pre-processing steps required, and with EEG, it would further increase. So that lag would be there. So we need to still explore more techniques that could reduce the pre-processing time in EMG and EEG based cases.
Okay, okay, thank you. So, and another question is like, what role does cognitive load or users fatigue play when using easy-based air lighting system?
So yeah, actually plays a lot of role actually. So we also did some experiment. It is not a part of the publication, but what we found is so anytime we recorded data when the user was fatigued, so the person would move a lot, so there'll be a lot of muscle artifacts, eye artifacts, and so on. Those would be there, and then we also saw that the performance in such cases, the performance of the system goes down tremendously. If the person is fatigued, or is thinking of something else, is his mind is wandering, and so on. So in that cases, definitely the performance goes down. Yeah, that is definitely there.
Okay, okay, okay. Uh, so another question. Mm, I think you already talked about this regional language input
Yeah,
apart from like English. So
yeah.
how it will be different? For example, and another thing is that how it will be different for cursive letters. Like you showed demo for, demo
Uppercase.
for very uppercase letters. So how it will be
Right,
different
right,
for
right.
lower letters and cursive writings?
Yeah. So, like for uppercase letters, because the vocabulary size would be 26, there are 26 uppercase letters. So, essentially we have a 26 classification problem. Uh, if we have to add lowercase as well, that makes it another 26. And then if we add digits like 0 to 9, so that would become 26, and 26 and 10, that would be like 62 classification. So the number of classes are increasing, and also there will be a lot of overlap between different classes. Like, so capital O, small o, and 0 all will look similar. So there will be a little bit more sort of merging of these different similar looking classes, uh, and the performance might go down. But then when we are doing full word level recognition, what we can do is we can first what we can do is we can have a layer of air writing which translates what's written to these some text, and then we can add a spell check layer to it, which can improve the overall word level recognition. No, you're
Yeah,
on mute
yeah,
actually.
yeah. No. So there is one question from Apurva Singh. I'll just read out your
Yeah.
question. Thanks. Hi, great presentation. Thanks for the methods and open source details. I have a question. Assuming the AI writing tool achieves a high accuracy for letters, would would the same model transfer to words?
Sorry, what would the
Same model transfer to words. Like if it is, we are getting high accuracy for letter recognition.
yeah, yeah.
So will it be like same for the words also or sentence?
So yeah, I mean, yeah, we can use the same thing for words by windowing. So for example, we have whatever, let's say 2 second windows, and then we can window and then predict individual letters, and then combine those individual predictions to form words. That is something that we can do. And then like it would, I wouldn't call it transfer learning per se, but it would be essentially windowing and predicting. So making small windows, predicting individual letters, and then combining those letters to form words. So like for example, for speech, as you know, we do phoneme level prediction and then combine phonemes to form words. So similarly, in case of this air writing, we would have to do letter level prediction and then combine letters to form words.
Okay, okay. So her actually her one follow up questions. She is like more giving more specific information to that. She is asking whether generalizing to words or sentence would require transfer learning. I think you have already answered that. If
Mhm.
so, how would that be possibly done?
Yeah, so just as I said, I mean, predicting individual letters and then combining those letter predictions to form words. That is how we can do that.
Okay, 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 great. I think Apurva got her answer. So I have one question
Yeah.
before taking a few questions from the Google form. So there is something when you, when we do the this kind of modality fusions, like there are lots of modalities will be there. Okay, for example, to get one output, for example, in your case, air writing recognition.
Yeah.
So now there is something called, right, the modality dropout. So while
Right.
doing that recognition, if one modality drop that, for example, some
Right.
noise came or something problem happens. So
Yeah.
how we can how we can handle in that situation?
Yeah, yeah.
Just
Yeah. I mean, so like the most relevant thing here would be, for example, because IMU is the most like the best performing modality here. So, like if we combine IMU, EMG, like as we saw, when I combined IMU and EMG, the performance was as good as one would have obtained when we just had IMU. So, for example, if we are doing IMU plus EMG and for some reason IMU drops out, then the accuracy would take the biggest hit. Like if EMG drops out, then that hit would not be that much. But with if IMU drops out, then there would be some hit. So what we can do is like from the literature, like as you said, the modality dropout is there, so we can have for example two different encoders for say IMU and EEG, and then during the time of training like in the this thing as I had I can say and share the screen again. So, for example, when I had this particular thing, so here, like during training itself, we can use a random modality dropout layer. So, where we are randomly dropping out IMU or EMG modalities. So, with some probability, say, let's say with the like 30% probability during training itself, we say that 30% of the times IMU is not available, or 30% of the times EMG is not available. So when we can train this model accordingly, and then of course, I mean the performance would definitely take a hit, but I think our model will be more robust in that case. We can make a more robust model.
okay, okay, thank you. Uh, I was one question. I, di- I don't know whether you you explore that thing. So what he is asking actually is that can we explore like cross model alignment losses? Like I think you explain about like Sinclair and some other
Yeah,
losses. So is
yeah.
there any possibilities of like multi cross model alignment loss or something like that? Because they are
So yeah, yeah. Yeah, I think, yeah, I mean, we can look at those. Like, I personally haven't looked at those for any of my work so far. But yeah, because I mean, what I would recommend is, I mean, the all the data sets are publicly available. So I would definitely recommend people to use, feel free to use whatever they think of. And that way, I mean, that was the idea of, making all these things publicly available so that people have different ideas because we might not have all the ideas at all times. So people
yes,
can play around with this, and like it is fairly easy to access from the GitHub repository, so
yes.
people can feel free to
So one question like where we can find a link to the GitHub repo and that I think what we'll do we'll share in the LinkedIn. So
yeah, yeah,
we'll
sure,
write a
sure.
LinkedIn post on our
Yeah,
I page and I'll
yeah,
just tag you
yeah, sure.
and then I'll just share all the
So
details.
yeah, I can
Share.
also share. So this is my like GitHub repo. So it
Okay.
is github.com/Ayush AYT. So here, like all these individual things are there. For example, Sclair. If someone wants to use the data, it is yeah, it can be accessed here. Like one data can be accessed here, or they can also reach out to me on mail. If uh, yeah, here. So, for example, here all the data is there, so you can see all the
Hmm.
data set is here.
Available.
Yeah. So this is for the first for the IMU based case. For the EMG based case, also this second repository one can take, and then can just go to this and then can download this data. And for the EEG based case, also one can uh, get data from this particular repository. So all the data, so everything can, so one can go to this GitHub, and then for different repositories, it's there.
Okay. Okay. And I was like, is it possible for you to share the slide also so that maybe you can link somewhere and then they can get them?
Yeah, I think
Is
it
it?
will be.
Oh,
It will be fine.
okay, okay. The last question, from my side is that, uh, there are multiple models are there for this kind of modalities already, like
Right.
EZ, then IMU and EZ. From Facebook, I think they have released some
Yeah, yeah.
cell-based models. So can we use that model? That is one thing,
Yeah.
and we can assume this. For example, if I want to do something for Indian languages, and we can
Hmm.
assume that as a uh, low resource task, and then we can
Right.
use that kind of model and we can use for is it possible or
Right, right. Yeah, definitely it is possible by like I think someone was saying transfer learning earlier. So
Mhm.
definitely like we can use the like keep some layers of those models fixed and then tune those models by using like limited data because say for example if you want to do say for example SMEs, so we might not be able to have lot of data, but we can record some data and then fine tune those existing models for uh, any other language that we can do. So that is definitely possible. Like yeah, and I mean I would also be happy to work with anyone who's interested in such
Yes,
things.
yes,
So yeah, happy
yes,
to collaborate and work.
yeah, yes, good. So I think we don't have any questions. Let me check in here. Just give me 1 minute. Yeah, so another question, like, so now you are using three modalities. Okay,
Right,
so this EZ, EMG, and IMU. Okay,
right.
so now when we, is there any kind of visualization you have done, like whatever, for example, we are learning some latent space. So that
Mm-hmm.
shared latent space, how it will look like. For example, if it is for single phoneme recognition, single, not
Mm-hmm.
phoneme, single letter
A
recognition,
little, yeah.
or if it is for a sentence recognition, how the latent space will look like, because how the time series will look like, because
Mm-hmm.
if I am doing I am writing a single letter, and I am
Mm-hmm.
writing a very cursive kind of letters, so how that
Mm-hmm.
kind of space will change if we learn from the data.
Yeah, so actually, I like specifically we're not looked at latent space for like words or sentences or those kind of things. But for individual modalities, I showed for the IMU and EMG case, we saw the latent space. So of course, for the IMU case, it was the like the clusters are very tight for different letters, even for different people when they write. So the clusters are pretty good. But for EMG, the clusters are sort of cluttered and they a lot of different letters overlap because of the noise and everything. Jointly for word level, as of now, we have not looked at it, but that is something like going from letters to words is a part of our future work that we want to do. Uh,
Okay.
yeah,
And what application you can think of this AI writing, apart from like we can
yeah,
write something?
yeah,
Is there any kind of applications like where, for example, if a healthy person can write very
yeah,
smoothly, for example, or who has this
yeah,
neurological disorder, he may not able to write properly
yeah.
in free space. So,
Yeah. So like I'll divide this into two parts. So one is how a healthy person can use it. So a healthy person can use it in two or three different settings. One is say a virtual reality headset someone is wearing, and we want to give full command input to the virtual reality headset. Then someone can write in the air, and then that can be communicated to the VR headset, and then that's how one can use it. Second would be if you are in a metro or airport, don't want to speak, so you can just write and then communicate and then send text messages or something. So and the other one is it can be used in defense applications, secure where someone wants to maintain privacy. So in those applications, a healthy person can use it. Where a person, so for if you look at someone some disability perspective, then we have so one case would be speech disability. So if someone has some speaking disorder and the automatic speech recognition systems are not performing well, then it can be used. The other one is if for people with some impairment to the wrist, or they only have a forearm, don't have the wrist, they can use this EMG based system. Or someone with some sort of neurological condition, or or some speaking disorder, that they can just use this EEG cap and then directly do this brain to text sort of thing. So those are the different applications where this can
Okay.
be used.
Okay. Great. Thanks. So Apurva has one last question. Uh, what would be the next future steps in this area with regard to improving the model accuracy or more modalities? So in terms of
So I don't like more modalities. Like I'm not sure if that would be a very good idea. But next steps would be going from letters to words, and then doing mixed cases, numbers, full word and sentence level. Those things would be the future thing, and then integration and deployment of this with the actual smart wearables and integration with VR headsets and so on. Those would be the future areas.
future, yes, yes, yes. Okay, so I think we don't have any questions, Ayush. Okay, so finally, like we are at the end of our presentation. Ayush, thank you for your nice
Thank you.
presentation, and it was very insightful and very interesting actually. Because for the first time, because apart from your PhD, because I know you from that time only, but directly speaking about that, so it's very nice. Uh, see you sometime. I was maybe in
Yeah,
this
sure, sure.
guys
Of
again.
course.
Maybe I
Yeah.
want to listen more about like your Harvard experience
Yeah,
sometimes.
yeah.
That,
Sure,
that
sure.
we'll just invite you for another session.
Sure,
Thank
sure.
you. Thank you,
Thank
guys.
you, sir. Yeah,
I'll
okay.
start
Thank
my
you.
stream first. Okay.